Good morning, it's Jim Vanderwall with the Fraser Basin Council. Thanks to everyone who's joined us so far. While we're waiting to get started and as other people join here, I'm just going to launch a poll. If you could let us know what type of organization you're with. We'll give people a few minutes because we still expect a few others to join us here. So hang tight and we'll start in a couple of minutes. Well, good morning, everyone. It's Jim Vanderwall again with the Fraser Basin Council. Just wanted to share the poll results with you so far for those who are attending. Looks like we've got a mix of folks from First Nations Administration is the biggest group from the staff, some consultants, as well as some non-government organizations that are joining us. We expect a few other people to join us as well over the next few minutes, but in the interest of time, I will just start with an introduction here. As I mentioned before, I'm with the Fraser Basin Council, and this webinar is part of our First Nations Home Energy Save series. And today we're covering building airtight homes. It's an introduction. You'll hear a little bit more about that in a minute. First Nations Home Energy Save is an initiative that we have working with First Nations communities and support organizations to try and help reduce energy use in homes and other buildings in communities, both existing homes as well as new homes. And so we do that through things like training webinars such as this one, workshops that are in person, other learning events, and do some pilot projects as well, trying to help work on some of the tricky issues involved. Just wanted to thank some of the supporters for this work, including the Real Estate Foundation of BC, BC Housing, the provincial government, and BC Hydro. There is a little mini website that we've created with some of the community success stories. If you go to that address there, and there's also links to recordings or presentations from past webinars. And so please do check those out. And if you're wanting to stay current, subscribe to our e-newsletter as well from that space. Just a few webinar logistics to start with. Everyone is muted right now, so we can hear our presenter well. But we do encourage you to ask questions. So there is a question box feature that we'll be using. We'll also be doing some more polls as we go along to help with some interaction. If you have any technical difficulties, there is an email there that you can contact, and I can try and help you out. If you're having difficulty hearing or whatever, certainly feel free to use that or any other issues. Hopefully you're able to participate over the course of our hour here. I did want to mention a link to this presentation. So we're going to be hearing from Albert Rooks in a couple of minutes. The workshops that he's talking about, we already have a couple scheduled. The first coming up next week is already full. Guasala and Aqueducts is hosting in Port Hardy. We are planning to have another workshop in Lindley Tenay territory in Prince George on April the 12th, and there'll be some other locations to be determined. As well, there are public workshops that are being hosted. So these two are the First Nations hosted workshops, which we've helped to facilitate getting Albert's team out there. But there are other public workshops that are available on their website for registration. And if you're interested in those, it's the same basic curriculum material. Just get in touch with me for the discount code for those, and you can register on that. There may be, we can't have workshops in every community, but there may be a community nearby. There are certainly a number so far already scheduled on Vancouver Island, Lower Mainland, some in the north, some in the Kootenays, and I'm sure there'll be other locations coming. So that's an opportunity. Just wanted to do a brief introduction of today's speaker. This is Albert Rooks, who's the president of Small Planet Supply, which is a company based in both BC and Washington State that provides access and education and training on energy efficient building materials and practices. And they also provide a number of different supplies and materials. And Albert's been involved in the kind of building of airtight homes at least since 2010 or so. And so he'll tell you a little bit more about that over the course of the hour. So I'll hand things over to you, Albert.
Great, thank you very much. Hopefully I'm audible, and is a airtightness training slide up. Okay, there we go. There's my trigger. Okay, so again, good morning, and thanks for the time to talk about this subject. My name again is Albert Rooks. I'm with Small Planet Supply, and I got involved in airtightness training in 2010 as some of the first passive house or step code 5 projects were developing in Seattle, Washington. And the metric for that application is 0.6 ACH, so really quite tight. And there was really no solid understanding of actually how to achieve that, other than some really basic steps of airtight drywall and some basic moves. Down in there, they're not even applying poly in buildings, so we don't have that material to work with as part of the current building. So I just simply went over to other parts of the world, in Europe and so forth, and saw what they did and started bringing those products and those styles of applications over to the US. And then when we started working in the city of Vancouver at that time was trying to help builders adopt the new code minimum of 3.5 air changes. At that point, all Vancouver building bylaw required a blower door test for all buildings, all new construction buildings in Vancouver. And so our mission was to build a workshop to try to help fill that education gap. And we partnered with RDH and some really good partners within RDH, James Higgins and James Bourget, and a couple of fellows there. You can see their names lower in the slide: Brandon Clevenger and Tim Bryant and Jeff Kirkpatrick, and they all have practical applications in the field, run projects, and have participated in the RDH just kind of study on achieving airtightness and publications like this. And so we began running the course. The course was successful, we think, we hope, and then now we're trying to help the course build across the rest of the province. So with that, I'll just do a brief tour of the course itself. And Jim, if there are questions pop up, that's fine. Jim can relay those back to me, and I'm happy to answer questions as needed. So an outline of the course, it's a one-day course, and essentially what we do is we bring a truck on site and we unload some full-size mock-ups that people are really going to work on. And we start a day, and the day starts with quite a lot of talking, because we really have to kind of build a foundational conversation about what it is we're trying to do with airtightness. You know, what's safe, what can create risks in buildings, what kind of materials can be used, and how it all really kind of fits in the energy step code. So the outline is essentially we start talking about the energy step code and where airtightness fits in, working with an energy advisor, which for much of the province is a new experience. What is an air barrier? More on that in a bit. And then once an air barrier exists, and how does it really fit into the house or a building as a system? And then we really start getting into specifics a little more about different ways to build an air barrier, different materials to use, some very specific building details on part 9, really part 9 focused. And then we talk about how that affects construction, sequencing, quality control. And throughout that, there's a couple of large blocks of time where it's examples and some hands-on training. So the way that we actually deliver this course is you can see in the back of that picture, kind of to the left of James, there's a small building. James has got his hand pointing to some of the lecture slides that we'll be looking at on a little pull-down screen on the other of the 2 mock-ups that we'll wheel into a space. The typical spaces that we're working with is hotel rooms, much like this, but really the best places are shops. Some kind of university shop where it's more of an educational institution. We just need spaces where we can roll the truck up, take these modules down on a lift gate and roll them into the building. Once we get into the hands-on phase, the first hands-on part of this application is to install a window, because at the end, really what we're going to do is seal up both of these huts, fill them with smoke with just a little simple fog machine, and then we're going to pressurize the buildings and learn where the leaks are. So everyone in the class actually participates, seals up one of the 2 modules, and then we get to just see how sealed up it is. It's never perfect. There's always leaks. That's why we have a blower door test, because it's not a perfect situation. It's always measuring a degree or a quantity of leaks. And where the leaks are really instructional. You know, so we start with a really basic understanding of we have no formal air barrier plan. We're going to add this thing called an air barrier, and then we'll apply that and we'll measure it and we'll see how functional it is. We work with a couple of different methods of applying the air barrier, and we'll look at that in some of the later slides. But here is actually, I think this was TRU in Kelowna, where we're able to roll all the equipment into the woodworking shop and host a class in the shop all day, starting at 9 a.m. and ending around 4 to 5 p.m. Sometimes we're able to hit kind of the 3:30 if the day goes really incredibly smoothly. And at the end, we seal up one face, the face that people have been working, going in and out of the building. We just apply the poly over it, tape it down. Everything else about that building is sealed up. And the interesting part is, since we're on this picture, the module on the left, where you can see the red tuck tape around the poly, you see no membranes or anything really on the outside edge of the building, the plywood sheathing on the left-hand side of the picture. And that's because that building relies entirely on the interior air barrier. And essentially we just take poly and kind of what we find in the province, that poly is started out as a vapor retarder and has turned into an air barrier. And we seal it up, tape up all the tops and bottoms and edges and plug outlets and things like that. So that's the air barrier there. We see how effective it is when we pressurize and smoke it. And on the other side, that other unit doesn't use any poly on the inside. There's none. And we use the membrane that's typically placed on the outside of the building, if it's suitable, like a Tyvek, Typar, something like that. There's a number of membranes out there that are better than just felt building paper. And we seal up those. In both cases, there's a window installed. The building has outlets and hose bibs and things like that. And all of those are potential leak points. And at this stage of the game, we're just starting to pressurize and smoke the building and see how they do. And that's really the exciting part of the course. But kind of jumping back to the beginning, as we start kind of in the morning, we acknowledge that we're really working on a step code, and that it's going to kind of roll out over time with different requirements as we go up, and that the final step 5 comes with a low air tightness number, and we'll acknowledge and talk about what that is. And what we really hint at in the early morning is that maybe there's a way that we're looking for some level of air tightness at a building right now. And by the time we get to step 5, that number is quite tighter. And there may be a fundamental change that we acknowledge, and we change really how we apply air barriers onto buildings somewhere in the middle. And we essentially maybe move from a system that's a little bit weak and a little bit problematical to something that is a little more reliable and a little simpler to apply, without bringing a bunch of new material on site, just using what we have and reordering what we have. And once we make that fundamental shift, then we're able to smoothly hit the requirements of step 4 and step 5. Because after all, air barrier work is simply filling holes. It's not really much more than that. So it's really accessible, it's really doable. It's just a different way of thinking about some of the materials that are being applied to the building. So we need to talk about the step code metrics and how all this, what the context is and how airtightness fits into the step code. So there's a brief conversation about airtightness and how it affects the MUI, mechanical energy intensity of the building, and the thermal energy density intensity or demand of the building, and what we're trying to accomplish when we get all these factors working together, which is essentially this really nice zero carbon building that has a really nice attributes and is wonderful to live in. I've done a retrofit that meets those standards, so I can kind of personally talk about some experience in that in the class. And then we really start looking at that there's really a lot of design going in here before we have materials showing up on site. And there's a design and an energy model and a plan of construction, and perhaps that green line of air barrier testing, or the air barrier itself, is maybe actually called into the plan specifications as you go and learn more about this, so that you've got something to execute as you bring out on site. We talk about how an air barrier is measured, and we talk about what the blower door does and what this lower right-hand corner ACH 50 means. And it kind of replicates, a modest windy day. So while it's a repeatable test to really measure the quality of the envelope, and therefore the expected heat loss through leaking of heat out of the building, or extra heat coming in on a hot summer day. In effect, this test is kind of also replicating what we experience throughout all 4 seasons on modest windy days. So as we move through the step code, we acknowledge that step 1 and those areas that are starting to work with step 1 really just start measuring. We don't have a number we're trying to hit. We're just trying to understand what number our current methods are bringing us. And from there, once we have an understanding, then we actually can think about the imperfections, some systems to change, some products to change, some applications to change. But we can really start a conversation at planning and on the job site to start addressing the leaks that we find. And therefore, the blower door test and the energy advisor, when they come on site with a thermal camera and so forth, is really quite helpful. Oh, sorry about that. See if I can figure out how to turn this phone off. That should do it. Yeah, sorry about that. Didn't even think that people might call me while I'm doing this. So in any case, we roll through the steps code. We look at the various levels of airtightness that we're really trying to hit, and we discuss plans on how to get there.
Can I just ask a question, Albert?
Yeah.
Maybe just 2. One is if some context for people. So for homes that are being built right now that aren't meeting any part of the STEP code, what would they look like for a new home? We certainly, I know from the older homes that we've worked with communities on, some of them might be, a double or more than step two in terms of how much air is leaking. But what would you say?
Well, it really varies quite a bit. I can say that in Vancouver, over the last few years, Vancouver would like you to hit 3.5 air changes, and it's really quite a struggle. We see a lot of fives coming in. It used to be, before we really started measuring these buildings, new buildings, current practices on both sides of the border, we'd see a lot of 7 air changes an hour, which is really quite leaky. With a lot of work, the averages started coming down to about 5 air changes an hour. And I say in the Lower Mainland, it's a challenge to move from 5 to 3.5, simply because it's such a big market and there are so many people that touch the building. It can be a bit challenging to change those steps. It's funny, as we head into various parts of the province and on Vancouver Island, both in the Kelowna, Penticton, Kamloops area, where quite often we see some 2 air changes per hour, some really quite good results. And it has to do much with the team, the local area, and the local trade connections that have been made, because in the end, most of the community is aware that it's really highly a measure of quality and it's a goal. And some have just naturally gravitated to building kind of better quality control in their building. But in short, to kind of back up on that question, if we see something in the 5 and 7, really in this climate, the house just leaks a lot of energy and becomes really uncomfortable. And traditionally, turn of the century buildings with balloon frames and so forth were in the 12 to 14 to 16 range. And those would be a building where you just need to supply a lot of heat, a big wood burning stove, some kind of intensive heat source and distribution, just to keep up with the loss that you experience in the winter. And when we get down to 2.5 and below, we get into buildings that, even if they aren't super insulated, they really don't lose a lot of heat. Its air barrier is much like just having a wonderful big, big jacket, big thick bubbly jacket, and failing to close the zipper up. Once you close up the zipper, the jacket really works, but without the zipper closed, it's a bit decorative. So in any case, hopefully that kind of puts some context on it. And so moving back in, working with an energy advisor, and the energy advisor at this point really becomes the friend to the building project, because the energy advisor, after doing all the modeling and the other aspects that the energy advisor is responsible for, is going to bring a blower door on site and hopefully a thermal camera or a smoke machine or something like that. And that's when you really get to learn and see what your normal practices, just being aware of an air barrier and working normally, that's where you get to see what that will deliver. And that gives you a chance to address it. Then we talk really about kind of the targets and what that means on buildings. And there's a line there that's kind of bolded that talks about what happens at 2.5 or 3.5 or 4.5 air changes an hour. And the differences on an energy model and just the thermal energy demand of the building. A building with 2.5 air changes per hour in current construction, if you reduce that air leakage, it has a certain thermal energy demand. If you make it leakier, right? If you drill more holes into it, and now it's 3.5, in order to have the same energy loss in the same condition, now you would have to have 3.5 air changes an hour and then add a couple inches of insulation around the building. Because it's 2 different knobs. As you tighten the air barrier, you're offsetting, you're losing less heat. If you don't tighten the air barrier, you have that heat loss, and in order to kind of retain the heat, then you bump up the insulation. So it's kind of a system of trade-offs. And at this point of the conversation, what we really get to, and I don't have that slide shown today because there's just, it's a full day class. Essentially what we want to say is that in order to get down to these really tight models or low heat demand buildings, airtightness, just the simple fact of taking something from 5 air changes down to 2.5 air changes is the most impactful on the energy load of the building and the least cost, simply because we're going to be reusing much of the material on site, just maybe ordering it in a different way. So it is really kind of the low-hanging fruit that we can work on across any climate. And what I find in the training and across the market is that it's really easy and very accessible. I showed this slide. It's a little Twitter feed from a guy building a passive house in Vancouver. And his point on this slide is that he's using a crew that has never done air barrier work before, and they hit this 0.6 ACH, and it's literally just totally achievable, thinking about planning a building in a slightly different way. So at some point we back up and we look at the basic barriers that already exist on the building, and we acknowledge that we're all really conversant in the water shedding surface and the thermal insulation, but we really don't talk about an air barrier. We talk about poly, we might talk about poly, and we really might talk about that more in the vapor retarder. Some might think of it as an air barrier, and those that think of it as an air barrier are farther along the pathway. And then we get into kind of discussions about vapor diffusion and how it works, and the dangers of double bagging a building or having 2 vapor barriers. And then we talk about the characteristics of air leakage and what that means on a building, and that the fact that multiple air barriers, different things stacked on top of each other, are a good thing in a building. And then we step back and we look again at all those barriers in the building, and we start asking ourselves, can those that already exist be turned into an air barrier? And is the job maybe selecting them and connecting them so that they are consistent all the way around the building? And then what kind of materials would we have on site to do that with? And we acknowledge that windows now become part of the air barrier. And maybe the job is just simply connecting all these parts together. At this point, we also really need to talk about the air barrier, where it is, what kind of materials go into it. So there's a whole group of discussion about that subject. We talk about that an air barrier needs to be continuous. It's very much like a bucket holding water. One leak is an air leak, and the goal is to find those leaks and systemize into a way that we can account for those leaks and close them out to the best degree possible. We look at what factors and what control layers air barriers affect in the building, and we talk about where it really interacts with water, air, heat, vapor, sound, and fire. And we kind of acknowledge at that point that the air barrier touches more of those control functions than any of the other critical barriers in the building. And we find, and we try to discuss further, that if we get the air barrier right, everything else about the building works so much better on top of the thermal energy demand and so forth. That has to do with interior health and comfort and distribution or dilution of gases and cooking smells and interior pollutants and things like that. The air barrier, combined with a good ventilation strategy, really makes the building work and comfortable, and has a lot to do with health. So why build an air barrier? There's a whole chapter on this, which is talking about condensation risk in assemblies, heat loss, indoor air quality, which is an important subject, thermal and acoustic comfort, and then really required by code and where it really fits into code. We talk about buildings like this. We spend some time there. We find that that there's an understanding that maybe this is a vapor problem or a liquid water problem when we see these blooms of mold and building damage. And as we dig into them and talk about how they're assessed and repaired, we really find that really issues like these are a source of air leakage. And simply, if we repair this air barrier and we create air barrier and systems in buildings that don't have these air leakage, issues, then we can add more insulation and we lower the risk of warm, moist air carrying water vapor into an assembly, encountering that cold sheathing on the outside, and then turning into liquid water and repeating that often enough to turn into building rot. So we look at various examples of that, and then we start breaking away into a hands-on activity. Simple hands-on activity in the morning is working with some new tapes that come from Europe with new acrylic adhesives, and taking a piece of wet sheathing and sticking the tape to it, noticing that it comes off easily because the board is wet, but then setting the board aside for a few hours until the end of the day, and then we do a pull test, and essentially what we find is that with these new tapes, they will let moisture dry right through the tape. They'll cure with water onto wet wood, and essentially now you can work with adhesive tapes on wet buildings in our climate effectively if we understand maybe the characteristics of various products sold by various companies and how to work with them. We roll back in to discussion points, and we start looking at the house as a system. So once we have an air barrier there, how it affects ventilation and mechanical. And when we create a solid air barrier, really what are the benefits that we get out of the heating and ventilation equipment? And there's a wonderful discussion to be had there. And how that differs from this, which is a classic circumstance as we open up buildings that have air leakage and the building gets depressurized when a bath fan is on, or a kitchen range hood, or a windy day. And because it's depressurized, it's going to pull makeup air into the building, and it's going to pull it through the leak pathways. And when you open it up, that's what the leak pathways look like. So it's a direct effect on health, and a statement that this is not really the best way to do things. And so it's further kind of support in what we're looking for in an air barrier, what we're trying to fix, and that maybe the alternative is down the road in step 4 and 5, we're building homes like this that have a really solid air barrier, and we find that even the bathroom fans are gone. All the ventilation needs are picked up by an HRV, which has some degree of filtration for normal circumstances, and even has the possibility to filter wood smoke out. And as we build these buildings, they're much more comfortable and much safer for the occupants, and they need less energy, and they have fewer drafts, which affect just everyone's health within the building. So further to that, we're back on looking at assemblies and how air barriers affect assemblies, how condensation works in walls. So there's a whole section on air barrier, vapor diffusion, air leakage into assemblies, what can happen with that. Because we're talking about buildings, we need to put safe building assemblies into context during the day. So on the left-hand side, we have a discussion going on the impermeable insulation and what can happen there if we have a vapor retarder on the inside and an impermeable insulation on the outside in a low insulative ratio compared to the cavity. And we compare and contrast that to permeable, more common mineral woolly type insulation materials that really kind of reduce that risk, offer the same thermal performance, but just kind of edit out the risk of condensation in the assemblies, and are very safe to work with. So we don't do more than really inform. It's up to the builder, designer, everyone in charge of the project, what types of materials they use. We just kind of talk about, some of the things to be aware of. And as we roll back into air barriers, we start talking about really practical application and the fact that in order for it to be successful, the air barrier is a complete line around the building. It can be on the outside, it can be on the inside, it can span a couple of lines, but it's quite literally taking a section like we're looking at, putting a pen or a pencil in one point, outside or inside, and continuing that line all the way around the framing of the building, or whatever we're going to define. In a vented roof, it would be under the trusses, without picking up the pencil. And if we have to pick up the pencil, then we don't know what's connecting the two parts together, or they're not connected, and that's something to address. When we can draw the pencil around across varying materials, all sorts of materials are involved, and as long as they're all connected and continuous, then it's a suitable air barrier. So we start looking at various approaches of spray foam, airtight drywall, sealed polyethylene, sealed sheathing with a service cavity. And we have a gauge down below. The top gauge is constructability, and so that's kind of an interpretation of what's reasonable and easy to build. And the lower gauge is airtightness. There's a whole series of these slides as we look at various approaches, and so we kind of try to measure, how easy something is to do and how successful it is. Just because it's easy sometimes doesn't mean it's going to be successful. So we spend some time discussing that. So that was an interior approach in simple form. And we acknowledge that we're using currently the third from the left, which is sealed polyethylene. That's kind of a go-to material. It's already on site. It's really there to control vapor, but we can employ it to control air because we can. And then we also notice that we have various materials and approaches that are possible in the exterior of the building. So we have the potential of sealed foam insulation taped off, membrane, Tyvek, Typar, something like that. We can actually even seal the sheathing with tape joints, and there are tapes that'll do that, and that is a straight up step code 5 passive house, one of the most reliable ways you can do it. We acknowledge that in other parts of North America, more in low-rise multifamily, liquid applied air barriers are becoming quite common. BC, they're not quite recognized, they're not quite in the market, and they're still a bit expensive for Part 9 work. But we talk about it because it's part of the subject. We talk about various products that can be used, tapes and membranes and sealants and so forth. And we spend some time talking about spray foam in windows, and that just does not work because the building changes and the foam doesn't change with it, and it's just not suitable. We have many examples of issues in buildings that are illustrated by air leakage and thermographic cameras. So we kind of talk about those, where those kind of pop up. And then we get into more hands-on. And the hands-on at this point will be to start sealing up those modules. So everybody spends the day up out of their chairs working on one or both of these modules, and one on the left is the interior air barrier approach. And so that's running poly around and dealing with light switches and outlets and pot lights and all that kind of stuff. And the one on the right that the group is standing in front of uses primarily Tyvek on one part of the building. Tyvek's on many of these job sites already. They're already taping the vertical joints to handle water issues, but the horizontal joints are left as a lap because the water can shed off of the lap. But the new step is maybe to put a tape joint, a horizontal tape joint, just with tuck tape, again, something that's already on site, and then calling that an air barrier. And we note in this section that we've got an air barrier in the left-hand module that's primarily on the inside. So we're coming up from the floor across the wall, spanning all the outlets and such, and hitting the poly at the lid, the underside of the roof trusses. And we're able to make that connection all the way around, but gee, we certainly have to seal a lot of things that are poking through the air barrier. On the right, it's cleaner, it's simpler, but it's all on the outside. And we need to seal the interior ceiling on the inside. So we have to have some way of joining those two together. And we talk about that in more detail. We do it with the hands-on function. And we have these same goals, and we start noticing that we have two possible pathways of achieving an air barrier. And one is working around the inside with poly and caulking and all the things that we're doing. And we notice that as we come up from a foundation, we have to swing around a floor system, back inside, go straight up, past some outlets and maybe some plumbing and who knows what else, and back up to a second floor, back to the outside, and then finally up the second floor and then connect to the underside of the lid. So that's one way. And another way that looks nice and clean is to work on the exterior side. So work at the foundation, go straight up the exterior of the wall with maybe some membrane that's already there, or in a very low result, like a passive house or step 5, maybe tape sheathing, which is a little more reliable than a membrane. And we spend some time talking about that, and we illustrate the differences, and we note all the issues that we run into on the inside and maybe how we do it. We've noticed some thermographic issues of, okay, spray foam may fill a cavity, but it doesn't connect the wall system to the floor. Then we start talking, having the same conversation on the outside. And we talk about methods and how inspectable it is and various things. And what's new here is that we need to connect that outside air barrier, which may be a membrane, to the underside of the ceiling. And so we talk about how to do that. And if we can do that, what happens? And then we actually note maybe the thing to do is to do both. The poly's already on site, the tuck tape's already on site, we're already sealing around E-boxes and things like that. The membrane's typically on site. The new thing is to add that connection from the outside to the inside. Maybe we need to get a little better on the inside. And so we start looking at, joining those two approaches, what would be needed, what process changes there are. And as we filled up, and we can acknowledge some of these issues that we find on the building site, the sequencing issues. But at the end, after we filled those 2 units with smoke, what we typically find is that the interior approach has got some significant leakage in the wall system, because it's just really hard to successfully seal around electrical boxes and the dryer vents and just all the things that are on the inside when we're working with poly and tuck tape. On the outside, it's easier and we can do it, but the common leak points that we find in both systems are all at the ceiling, right, the lid. And this part of the building is consistently the same. It's consistently has more penetrations per surface area than walls do. And it's prone to leakage. So we find that if we can get the wall systems working better by working on the outside or the inside, and what we do find is that while working on the outside and the inside, pretty soon we probably get pretty good at the outside, and we may not need the poly at all anymore. And poly, we recognize, we go back to the origin of poly, and poly is there for vapor diffusion. So we recognize that, okay, we're trying to use something that's kind of a difficult material to work with in a difficult place of the building that's really tasked and really implemented there to handle a different task, which could be accomplished by vapor retarding paint on drywall. So we recognize that, and we recognize the fact that at some point in the building and the contract and the production of the buildings as we go forward, maybe we just don't need poly if we can get really good at working on exterior air barriers. And we kind of proved that out in the class. And then the thing to focus on is this lid, and to start looking for better solutions for lighting, LED lights that you can't hold them up, and even though they have an airtight rating by the industry, you can still see through the body of the light. And so we start recognizing that even though products are rated to be used in a certain application, they're not really functional. So we do our own investigation, we start selecting our own products and really getting better at that, and thinking about how to handle partition wall interconnections with ceiling poly or membrane. We may change at some point in the life of our business and our business plan that we not use poly for lids anymore. We find something more suitable. There's a lot of products out there that do a better job than poly. Some of the step code or passive house builders even use plywood and OSB to do that. But we just find some better products better ways of accomplishing this. Oh, and there I am, back to the short end of my slideshow. So I'll leave this slide up. And at the end of the day, what we've done is we've talked about air barriers, where they fit into the step code, how they affect the building. We look at what's really on site already, maybe some new things that can come on site, but we try to really keep the added material issue off the table, because it's really what we find, and what we find with the actual blower door test with these two modules, is that it's reordering materials on site that are largely responsible for other aspects of the building, but they also can function quite well as an air barrier, and it's not hard to connect it all the way around the building. And then maybe adding just a few products that are special. Some are common, like just EDPM, very flexible rubber sheets that can be used on wiring and hose bibs and plumbing stacks and things like that. And it's actually really not hard to make these air barriers in a simple, cost-effective way. And at some point, then we're really talking about the construction sequencing. Maybe someone's job on site is now different. Maybe there's an air barrier boss, or somebody that's really designated to think about that project and its air barrier and talk to trades as they come out. And when they see the electrician or the plumber pull the chainsaw out of the truck, then it's like, okay, hang on, let's talk about what we're doing, and we can do what we need to do. We just need to do it in a way that I can get it sealed up and have a functional air barrier. And that person can be, in our experience, in our discussions, that person can actually be one of the youngest, newest, lowest cost person on site. It gives them a chance to kind of chase a quality scenario on the building, gives them kind of new information to work with, and potentially they have some value that they can bring to their job and their trade, and perhaps it creates a ladder upwards within the industry, because the industry is really changing as we move from simple prescriptive practices into measured performance-based practices. And it really gives us a chance to kind of change the game, bring new tools, and have the freedom to think about new ways that we can reach our performance targets, rather than just kind of stuck using existing ways and fighting kind of an economic model. Once we switch over to performance and energy, be it air barrier or mechanical systems, the industry becomes really quite interesting. And hopefully, at least on air barrier, we can do that without adding significant cost. So at the end of the day, we go through an evaluation process, we have more conversations, and then we award some documents which allow people to apply for their CPDs, and then we strip the mock-ups down and close up the day. So with that, I'm at 11:50, so we've got a little bit of time for questions, and I think I've kind of hit the subjects in a relatively light way across a full day class.
Great. Thanks very much, Albert. That's a great overview, and I think some interesting new concepts for folks who are on the line. So while you're thinking about your questions, just wondering, for those who are with communities, who builds homes in your communities? Is it community-owned company? Do you bring in outside contractors? Do you have prefab buildings? Just be interested in that, because I think that it's important to think about who's building the homes, and that's obviously where some of this training needs to be directed. So while people are filling that out, Albert, one of the questions that's come up is, does this course include ideas around retrofitting of existing homes, or is the focus on new construction? I think I know the answer, but maybe you can speak to it.
Yeah, the course as written is focused on new construction. I've done retrofits myself, uh, and much of what we're talking about is applicable to retrofit. And the course is really a discussion, right? It's not, someone getting up and just rolling through a set of slides and that's all we can do. The course is really looking to create a conversation, be it new construction or retrofit. So if there is the desire and to have a conversation about retrofits, then there's plenty of room for that.
Great, thanks. I'll just close the poll here and share the results. So it looks like quite a few folks, 44% responses. People are, there's a community-owned construction company involved. In other cases, it might be an outside contractor, about 22% of the cases, and all the above for 33%. No one indicated prefab, at least for this group that's here today. So that's always useful to know. And obviously, if there are people who are using community-owned companies, that's a great training opportunity. The workshops that are coming up. Just hide that result. And we do have a question here from Tom as well. They need to do a lot of building envelope renovation work, and they're a little worried about increasing air barrier performance at the risk of reducing interior air quality and higher humidity. So that this is Tom's from Lilwat. And is this something to be concerned about? Any strategies to consider?
Well, it is. It is definitely something to be concerned about. And it's a little bit of a double-edged sword, so I'm going to be very careful about this. Ventilation needs to happen within the building in order to manage indoor occupant health and the building health itself, regardless of a good air barrier or not. Without a good air barrier, the occupants will be having more access to fresh air and so forth, just depending on the weather conditions and so forth. But the building will suffer, which will come back and affect the occupants because as you create more mold and issues within the wall cavity in the building itself, sooner or later that'll reach back inside and permanently and dramatically affect indoor air quality. So in my way of thinking, and certainly our recommendation is improving the air barrier, get it functioning right, which will improve the building and the long-term health of the occupants as they're affected by the building itself. And at the same time, there really has to be a plan for ventilation. And in new buildings today, hitting any of these low targets, the code talks about a principal fan, and I'm aware of kind of what the values are. And there is provision in the code to properly ventilate a building. But in this climate, HRVs are really not that expensive. And an HRV compared to a bath fan can be put into a building for a pretty darn reasonable cost. I work with some HRVs that are full-on passive house buildings, and they're really quite effective. But even the basic HRV, the goal is to keep a fan running 24/7 and recover some of that conditioning energy that you've put into the building, either by heating or cooling or something like that. Even at a modest 65%, it becomes meaningful, and it's really quite important. So I strongly recommend it, and I would recommend it with heat recovery ventilation that's on 24/7, good for the occupants and good for the building. Jim, if you're talking, I don't think we've got anything on our end.
Sorry about that. I guess I was muted. Yeah, sorry. I was another question here from Leo about if there's funding available to pay for energy modeling, or there are examples for different zones that people could look at in terms of maybe typical homes that are built out there. You have any thoughts on that, Albert?
Funding for energy modeling, it's outside of my area of expertise. The modeling cost on buildings at least isn't, it's not a terribly large number. I would imagine there is, but I have to plead ignorance on this one. I'm pretty closely tied to the technical and the air barrier work, and I think I'd have a hard time understanding what funding is available out there. Sorry.
Sure. No problem. Yeah, I think, Leo, my feeling would be that probably in many cases it would be possible to get some funding from utilities for that if we're talking about new construction, depending on where you are, Fortis or BC Hydro. And potentially, those kind of costs could also be considered for other funding programs that support housing. Of course, we know that the funding that's available for First Nations housing is always, inadequate, and so adding additional costs into those formulas can be problematic. But if it's something that you're looking at for new homes, then certainly let's follow up on that and see what we can find. I've worked with some communities where you have been able to get some utility funding to support that, and I think it's quite important and relatively small cost with a good impact, because it's going to impact the whole design of the home. Other questions? One other poll here, maybe just for folks to think about, get a sense of. We talked a bit about retrofits, but for new construction, how many homes are planned in your community in the next couple of years, just approximately? I'll just close that and share the results as well. And yeah, it does look like quite a few communities that are participating. We've got new homes planned in the next couple of years. Some of them quite a few not any at all. But I think that's indicative of there are a lot of new programs supporting housing because of the extreme shortages, and so some good opportunities here to increase the efficiency of those homes for the new occupants. Well, it looks like we don't have any other questions at the moment, and we're just coming up to 12 o'clock. So I think we will wrap things up here. Thanks everyone for participating in our webinar today. And we will be able to share further information with you if you're interested. There's in the slides, I'm sure we can get those. And as well, if you're interested in participating in a or some of your staff or others that you're working with, contractors participating in upcoming training, please do get in touch, and we would like to make sure that either that a training session can come to your area, or if there's an existing one, that we can help to support some of the costs for that. So thanks, Albert, for the great overview presentation. Much appreciated.
Great. Thank you. Happy to be here.
Okay. Have a great day, everybody.